So let me just say that this stuff is complicated. I recorded a whole audio for this, and luckily the quality got screwed up, so I get to do it again. So this is a voiceover, and I'm going to talk about how to develop shaders in Weirdo Studio. If you like this video, you should wait till you watch it and see how complicated it is. But if you like it, click like, add a comment, because if enough people want to, I'm going to add a video series about shaders. And fret not, the regular Weirdo Studio tutorials are coming too, and those won't talk about shaders as much. They'll just talk about regular old tutorial stuff. I will be resuming that, I promise. I just wanted to experimentally see how many people were interested in learning how to develop shaders in Weirdo Studio. So for starters, in my Learn How Graphics Work video, I talked about how everything in 3D graphics is made out of polygons and points, which those polygons are made out of. And the job of a shader is to convert those points that are in what's called model space or 3D space to 2D space that you see on the screen. And there's a lot of series of mathematical work that's involved with doing that. And that work used to be done automatically for you by OpenGL, but as game engines have gotten more advanced, they've allowed programmers that have knowledge of programming to actually write that code that runs on the GPU. And that code is commonly called a shader. And it's written in a language called GLSL, which is very similar to C. If you don't know C, I recommend you watch my C videos if you're interested in learning how to do this kind of programming. If you don't care about programming, this might not be a video for you, but if you're interested in learning how to make games, 3D games, and more specifically how shaders work, then check this out. So as I'm showing you here, all the shaders in Weirdo Studio are actually written in GLSL, and Weirdo Studio actually allows you both in the iPad and the Mac to create your own shader by clicking Use Shader and giving it shader code and directing how it works. And once you get those shaders written and all nice and pretty the way you want them, they're actually saved with the scene file, and you can share those shaders with anyone else on your team that's making a game. You can develop the shader entirely within Weirdo, and then you can ship it to an actual game because it's using production GLSL, which is OpenGL shading language code. I've already used this feature quite a bit in the game I'm working on right now. So I'm going to create a shader here and just call it my shader because it's mine. And immediately people will see this, be like, oh, I want to create a shader, and then they'll be presented with code, and they'll be like, what the hell, and they'll be scared away, and they'll immediately close it. So like I said, shaders are actually written in code. But it's not the most scary code in the world. If you know C, GLSL is quite easier than C because it's much more restrictive. It's got special data types. The more commonly one that everyone knows is already is float. Shaders deal heavily with floats, but special kinds of floats as well. So you have the normal float, which is just a scalar, just a regular number. But you also have Vec2, Vec3, and Vec4, which are two-dimensional, three-dimensional, and don't scare you, four-dimensional floats, which have .x, y, z, and w for the four-dimensional case. You can think of them kind of like structs, but they're real primitive low-level types that are ran on the GPU hardware. You also have mat2, mat3, and mat4, which are 2x2, 3x3, and 4x4 matrices, which do matrix math for you, thank God, on the GPU, and allow you to multiply matrices which perform 3D transformations for you directly in the shader code. Both Vertex and Fragment shaders are the two special shader types that make up an entire shader, and both those stages. There's other ones, but Vertex and Fragment are the ones that are the most important. They're required by shaders to have at least both those stages implemented. The Vertex shader's job is to shade or process one vertex, not all of them at once, just one vertex at a time. Every vertex is shaded or ran through the Vertex shader and parallel, theoretically, with respect to all the other ones. So you can only access one vertex at a time in a Vertex shader. Fragment shader, on the other hand, fragment is a fancy word for pixel in GLSL or OpenGL. And the Fragment shader's job is to shade one pixel. You can only access one pixel at a time. So you'll immediately notice there's this function called main in every shader. And that main function is basically the actual function that's ran where your shader code starts once again for every vertex in the entire shader. And the job of the vertex shader is to take inputs, optionally create outputs, and more importantly, compute the GL position, which is basically the projected clip space, or you can think of it as screen space, two-dimensional like position of the vertex. Its job is to take the 3D vertex and transform it so that it goes in the right place. And in Weirdo Studio, I provide information that you need to make the shader work automatically for you via what's called system inputs and system uniform variables. An input to a vertex shader, it's also called an attribute, is information that the vertex shader needs about every single vertex. So every vertex will have multiple attributes. The most important one is the position, which is, you would think it should be a vec3 for 3D, but it's actually 4D. You don't have to worry about this too much, but basically it's a three-dimensional point position with a special W component, which is used just to make perspective projection work right. Told you this was complicated. After that, you've got the normal, which is the normal vector, simple three-dimensional normal vector. It's used by the lighting. And you got the tech chord, which is the texture coordinate, UV tech chord, which is used for texture mapping. These names, position, normal, and tech chord 0, are system attribute names that are defined by Weirdo Studio. You can read up all about all that stuff in the Weirdo Studio shader programming guide, which is in the user guide. And it explains what the system attribute input names are, and more importantly, the uniform ones. So an input variable is, like I said, an attribute on a vertex. A uniform variable is the same for the whole model. So for the example of the sphere, uniform variables are the same for the whole sphere. Like I said, there's special system names for uniforms that will give you information that you need from the Weirdo Studio graphics engine system for you. The two used here are the model view projection matrix and the normal matrix. Those matrices, don't get too scared by the word. The job of a matrix in 3D graphics is basically to transform or to put a vertex in the right place, transform between two coordinate systems. The most common coordinate systems that a vertex shader needs to deal with are the model space, which is the space that basically shows the center is the center of the object, and it basically revolves and is around its own local origin, which is its own local 0. View space, which is basically what you're actually looking at in 3D, which is basically what the camera sees. And that positions the model to its where you see it on the screen. And then, of course, projection or screen space, which is the result of the two-dimensional projection on the screen. And like I said, the job of the vertex shader is to take the position, run it through that giant transformation, and put it on the screen. And that entire transformation is composed in the one matrix called the model view projection matrix. And it's all done, calculated and given to you automatically by Weirdo Studio. So that model view projection is the two transformations in one that you need to do that. And you just multiply the model view projection matrix into the position, and that does the transformation for you. And that's basically the most you need to think about that. And every vertex shader, that aspect is essentially the same. GL position is almost always just set equal to the model view projection matrix times the position, unless you want to do anything fancy. So that part's basically just there. And for the normal, you basically do the same thing, except you multiply the normal matrix times the normal. And that's basically does the same transformation, but with a few extra steps so the normal doesn't get screwed up by scaling. And like I said, that normal is an output, or it's called a varying variable of the vertex shader. And anything that's an output of the vertex shader, or any shader stage, goes to the next stage of the shader pipeline. So the output of the vertex shader becomes the input of the fragment shader. And for that reason, those types have to be the same. You can think of it as like you're handing data off. So if you compute something like a normal, a transform normal for every single vertex point, then as the polygon gets shaded, then a interpolated or mixed version of that data will get passed to every single fragment or pixel that gets shaded by the pixel shader or the fragment shader. So that's the Vertex shader. It's really complicated, and a lot of people do not like to deal with it at all because it's so complex, but it's truly where all the 3D math at least starts. And other shader systems like Shader Toy and stuff will completely leave the Vertex shader out and only go with the Fragment shader because it's a little easier to think about. And I always feel like they're missing half the picture when they don't expose that. So the Vertex shader is it's good to have. I also wanted to comment and say that this stuff with Weirdo Studio is all templatized. So when you create a new shader, you don't have to start with all this stuff from scratch, which is awesome because that would suck. It starts and loads the basic lighting shader template for you automatically, and if you click that load button, you'll see all the other possible types of shaders that you can load into Weirdo Studio and learn from, which is always nice. Yeah. So what else do I need to talk about here? I talked about main, I talked about the normal, talked about the transformations. I'm going to go into all that stuff more in detail if I decide to do a shader tutorial series because the stuff's way too complicated to talk about. So yeah, I'm just showing you all the possible templates there. So now that we've got the Vertex shader, we need to actually shade the pixels. So we've processed all the vertices and transformed them in the way that into screen space. Now they will start being filled, and there will be pixels filled in or shaded for every single triangle that actually shows up on the screen in 3D space. And that part is handled by the second stage, or the final stage of the shader pipeline, which is called the Fragment stage, or the Fragment shader. So the job of the Fragment shader, just like it is the job of the Vertex shader, is to shade or compute the color of a single pixel. So just like the Vertex shader can only access one vertex at a time, a pixel shader can only access one pixel at a time. And usually that pixels are computed in parallel on the GPU for you. So you really can't think about anything except the current pixel. And the only inputs to the Fragment shader are the outputs of the Vertex shader or whatever shader stage came before, which is typically the Vertex shader. So the first thing you'll notice is the in. There's an in variable, which is the same vec3 type of the computed normal, which is the normal at that given point of the surface corresponding to the pixel that you're shading. I've also, I don't know if I already mentioned this, but medium P, high P, those are all for iPad and OpenGLES mobile stuff. I'm not going to talk about those. You can kind of ignore them. You can even actually take them out. Well, I wouldn't recommend it, but you can definitely ignore that they're there for this video. So, the VA normal is computed by the Vertex shader and handed to the Fragment shader. And as I mentioned, or maybe didn't, normals are needed to do lighting. So the normal is brought into this shader. That's an input. The only output of the Fragment shader is the Frag color, which is a vec4 RGBA for the color of the entire pixel, which is computed. The lighting is done by those 4 lines there. It's basically standard dot product between the normal vector and the vector to the light, which happens to just always be staring right down the center. So you'll notice the light shining directly on the sphere for the shader, meaning that the outside is dark because it's around the edge, and the light shining right in the center, it's a lighter color. Lighting is very complicated, so I'm not going to talk about it too much here. And I'm just going to show you that happens if you set the fragment color directly to a constant color. So if I just set it to red here and hit build or Command B on the keyboard, you'll see that the shader is now showing red, which basically means every single pixel is just set directly to red. And that's basically a basic fragment shader for you. It's, like I said, a little easier to think about fragment shading than vertex shading. That's basically what it looks like. There's a ton more I could talk about with shaders here, and I'm going to avoid doing that until I get into a series if I do. But if you guys want me to elaborate on this stuff or start a new series, just comment or like this video. I'm going to show off uniform variables here, so I'm just going to go ahead and create a variable called color, vec4, and declare it as a uniform up top. And now I'm going to use that variable instead of computing or just manually putting the color in. And you'll notice when I hit build, it'll be using the color that is actually set by the uniform properties in the UI, which is really neat. So if you wrote a really neat shader and you shipped it with the scene file and you send it to somebody, you can always parameterize your inputs to the shader. Just like here, I set it to green, and it uses that color from the UI. So that's the way I'm making complicated shaders more easy for people that don't know shader code to work with. You can even copy the shader to the clipboard, paste it into another scene, and use it wherever you want, which is really neat. Once you get your shader all nice and done, you can really use it anywhere and basically use it to develop games. You know, as a proof of concept for a special effect, for a 3D shading effect, you can develop it completely in here and ship it around. And that's what I'm doing with the game I'm actually working on right now. I'm actually doing quite a few shader effects in Verto, and then I don't even have to do anything except load them when I'm in the game. As a final example before I stop, I'm just going to show you guys what happens if I actually access the special GL frag chord, which is a vec2 position of the fragment chord itself in the screen, like where the X position of the pixel is. And I can actually use some neat little sine wave math on that to actually show off a neat little effect besides just a boring color. So this is just kind of like the Hello World shader effects of, you know, a stupid frag chord sine wave. So that's kind of cool. Well, I don't want to make this video any more complicated than it's been, so I'm going to go ahead and end here. Thanks, guys.